In this presentation, I hope to help with the confusion of the Foucault pendulum by looking at the physics of the Foucault pendulum. Back in 1851, Leon Foucault used his pendulum to demonstrate the Earth's rotation about its axis without relying on astronomical observations. The precession of the plane of the Foucault pendulum swing demonstrated the rotation of the Earth. Now, the Foucault pendulum is basically a spherical pendulum with very small swing amplitude, except that it's perfectly decoupled from its mounting fixture in the axial or vertical direction. The swinging motion of the pendulum ensures that the angular rate in the vertical direction is zero. Now, about 100 years later, in 1952, Alexander Ishlinskii published his solid angle theorem. This presentation contains the explanation of the pendulum's precession by applying Ishlinskii's solid angle theorem. This is a figure of the Earth rotating on its axis and a pendulum that is initially oriented in direction A and direction B as the Earth rotates by angle lambda. The pendulum axis aligns with a radial vector that originates at the center of the Earth and extends to its surface. As the Earth rotates about its axis by angle lambda, the pendulum's axis moves from orientation A to orientation B. After a complete revolution of the Earth, when the Foucault pendulum gets back to its original position, the induced rotation is equal to the conical cap, the solid angle of the conical cap, of the latitude north of the pendulum's location. So basically, any vertical axis on the surface of the Earth has two sources of axial rotation: the component of the Earth's angular rate along the vertical axis multiplied by the elapsed time, and the second component is the solid angle swept out by the vertical axis given by Ishlinskii's solid angle theorem. After one complete rotation of the Earth, the angular rate component is 2 pi times the sine of the latitude. And the solid angle component is 2 pi times 1 minus sine of the latitude. That's the solid angle component given by Ishlinskii's theorem, which is the area of the conical cap north of the pendulum's latitude. The sum of the angular rate component and the solid angle component, when you add them up, it's equal to 2 pi, which simplifies things. So every vertical axis in the northern hemisphere rotates by 2 pi in the counterclockwise direction. And an Earth-fixed observer standing on the Earth, standing in the vertical precession, also rotates by 2 pi along the vertical axis. Now the pendulum has only the solid angle component, which is 2 pi 1 minus sine of the latitude. An Earth-fixed observer sees the pendulum rotate by minus 2 pi sine of latitude. So he's seeing that rotate in a different direction. Now this figure shows for intermediate angles all the way out to 360 degrees of Earth rotation. It shows you the mounting fixture, which is the black line, and the Foucault pendulum, which is the red line. And this is for a pendulum located at latitude 30 degrees, where the pendulum's rotation in the counterclockwise direction is 1/2 of the mounting fixture's rotation. So you can see it's 1/2 there. Now here's a demonstration. If you're looking down the vertical axis from top to bottom, you can see both the pendulum orientation and the mounting fixture orientation. The pendulum is the red line, the mounting fixture is the blue line. And this is when we start out at t is equal to 0. After we rotate, the Earth rotates 180 degrees. Roughly 12 hours later, the mounting fixture rotates 180 degrees in the counterclockwise direction, and the pendulum rotates 90 degrees in the counterclockwise direction. But if you're with the mounting fixture, it appears as though the pendulum is rotating 90 degrees in the clockwise direction. And that's what's observed when you're watching the Foucault pendulum. After a full rotation of the Earth, 24 hours, the Earth rotates 360 degrees, the pendulum only rotates 180 degrees. So if the observer sees the Foucault pendulum rotating 180 degrees in the clockwise direction, and that looks like the precession that's observed. Now, the interesting thing is, if we reduce the amplitude of the swing of the Foucault pendulum, it still rotates like a normal Foucault pendulum when it has zero swing amplitude. But it has to be initialized with zero angular rate in the axial direction. And in order to do that, you'd have to start out giving it a rate of the Earth angular rate omega times the sine of latitude, but in the opposite direction, in the clockwise direction, for it to have zero axial angular rate in the inertial frame. That's because everything sitting on the Earth's axis at latitude L, at a latitude, has an angular rate given by the Earth angular rate times the sine of latitude. So to get it to stop rotating, you have to rotate it in the opposite direction. After one Earth revolution, the pendulum rotates according to Ishlinskii's theorem, 2 pi times 1 minus sine of the latitude. So now, since the zero amplitude pendulum has zero velocity with respect to the Earth, therefore it has zero Coriolis force. So we can conclude that the Coriolis force cannot explain the precessional motion of the zero amplitude Foucault pendulum. So that indicates that the Coriolis force is not the fundamental cause of the precession. So we can conclude, after one Earth revolution, the Foucault pendulum rotates about the vertical axis in a counterclockwise direction according to Ishlinskii's solid angle theorem, which is given by 2 pi 1 minus sine of the latitude. An Earth-based observer rotates 2 pi in the same amount of time in the counterclockwise direction. So that person would see the pendulum precessing by minus 2 pi sine latitude in the counterclockwise direction, which is equivalent to 2 pi sine of the latitude in the clockwise direction. So I hope this clears up the motion of the Foucault pendulum, because it was a very complicated subject and people are quite confused about how it precesses, why it precesses, etc. Hope you liked this little presentation. Thank you. Bye.